wait for one more minute before we start, just to make sure that everybody's here. Okay, so anyways, this is the second panel of the photospheric emission of GRBs. So yesterday we had very interesting talks and very interesting discussion, and today should also be quite interesting. So we have two talks based on numerical simulations, and then it will be more data-oriented discussion. All right, so I guess maybe we should start. So then, Hirotaka, I think you're the first speaker, so please go ahead. You are muted. So we cannot
Sorry, yeah, I'm now trying to share my screen again. Oh, do you see my presentation? No?
Yes, we see your presentation, but it's not
full
screen.
How?
Yeah, now
do you see it?
Yes, absolutely.
Oh, it is? Okay.
Yeah.
Do you see my mouse cursor?
We do, yes. Well, I.
Okay, sorry. Okay. So, okay, thank you. So should I start the talk?
Yes, please go ahead.
Okay, thank you. Hello, everyone. I'm Hirotaka Ito from Riken. First of all, I'd like to thank the organizer for giving me an opportunity to talk in this session. So today I'll talk about my study on the photospheric emission based on the numerical simulation. So this is one example of the simulation, which is showing a relativistic jet digging through the massive stellar envelope. And based on such a simulation, we perform a radiation transfer calculation to evaluate the photospheric emissions. Okay, so let me start my talk by simply, showing the, starting from the introducing the motivation of my study. So as presented in the yesterday's session, as you know, photospheric emission is considered as one of the leading models for the emission mechanism of GRBs. So in this scenario, so if we consider a jet that is propagating through a massive envelope, it is quite likely that photon will propagate through a dynamically evolving jet, which possess a structure far from the simple top hat-like shape, and such structure should be imprinted on the resulting emissions. So in order to assess such an impact of the jet structure on the emission, one needs to consider the global dynamics of the relativistic jet, as well as radiation transfer within the jet. So in our study, we explore this issue by conducting a Monte Carlo radiation transfer calculation based on the hydrodynamical simulation. And our numerical method is basically identical with the MC-wrapped code developed by Davide and Tyler's study, which was presented in the Tyler's talk yesterday. Okay, so let me move on to the detail of the study. So we conducted the simulation in the context of long GRBs as well as short GRBs. And the first part of my talk will focus on the simulation of long GRBs. So this is the setup of the simulation. First, we calculate the evolution of the relativistic jet breaking out of the massive star by performing a hydrodynamical simulation in 3D. Initially, the jet is injected at the center part of the star, and its evolution is followed up to the point it breaks out the star and up to the point until it becomes optically thin to radiations. The considered progenitor star model is widely used Wolf-Rayet star model taken from Woodsey-Higa 2006. And here, as for the jet parameters, we employ the values shown here, which is in the range of typical values employed in the literatures. So in the current simulations, we consider 3 models with different jet powers shown here, which covers 2 orders of magnitude. Okay, so after solving the hydrodynamical simulation, as a post-process, we solve the radiation transfer using Monte Carlo method. And initially, we inject the thermal photons deep below the photosphere, and we compute its transfer within the dynamically evolving jet until it will be eventually released at the photosphere. So this is how we evaluate the photospheric emissions. So, okay, so now let me move on to the result of the simulation. Okay, first let me I'll show the result of the fiduciary model, which I employ a medium value for the jet power among the three models. Here is a snapshot of the 3D hydrodynamic simulation with a 2D slice at the central axis. And as you see, initially jet digs through the massive envelope. It eventually breaks out and it propagates to large distance, and finally it will leave the star. And at this latest stage, most of the emission will be released. Okay. So, and this is resulting light curves and spectra, which is the color representing the difference in the viewing angles from the jet axis. Since we inject the steady jet at the center, all the time variability imprinted in the light curve is coming from the purely jet-stellar interactions. Looking at the spectrum, although we inject the thermal photons initially and also only consider thermal electrons as a scatterers, the resulting spectrum shows a broadened shapes due to the geometrical broadening effects, which I believe was introduced in yesterday's Azaf talks and also Tyler's talk. And primarily the broadening at the low energy band is coming from the multicolor temperature effect due to the superposition of emission arising from the different location of the jet which has non-uniform structures. And on the other hand, the broadening at the high energy part of the spectrum is coming from the effect of the bulk comptonization in the sharp shear structure within the flow, primarily at the shock. It is noted, however, that this bulk comptonization effect is likely to be artificially suppressed due to the lack of numerical resolution. So since we have to cover several orders of magnitude in space in order to resolve the photospheric radius, we do not have sufficient resolution to resolve the fine structure within the jet. So in this sense, we should this result should be considered this non-thermal feature should be considered as kind of lower bound for such a features. But anyway, the main message here is that the spectral broadening is likely to arise from the geometrical broadening effects, even in the absence of the non-thermal particles. Okay, so another important feature found in the simulation is that the viewing angle dependence of the spectral peak energy and luminosity. This is due to the lateral structure of the jet. As a result of the jet-stellar interactions, jets have a powerful core at the powerful fast core at the central region, which is surrounded by slower decaying wing regions. When the line of sight of observer is aligned with the core angle, the spectral peak energy and luminosity is insensitive to the viewing angle. But if you go to larger viewing angle and if you start to see this wing region, the peak energy and luminosity sharply decline with the viewing angles. And this viewing angle dependence results in a correlation among these among the two quantities. Okay, let me mention the dependence on the jet power. Here I'm showing the snapshot of three simulation of three different models, with center being the fiduciary case that I have just presented. And the left panel shows the lower jet power model, and the right one showing the higher jet power model. As you can see, when the jet power is weak, due to the lower thrust, it struggles to break out the star, and the kind of global wobbling feature is seen in the resulting jet structures. On the other hand, if even the jet power is higher, its propagation becomes more ballistic-like due to its higher thrust. So although the dynamics shows some difference, roughly speaking, the emission features are similar among all three models. The features found in the fiduciary case is found in all the two other models, and the main difference is that the spectral peak energy tends to be higher as in the higher jet power cases. So the viewing angle dependencies also show a similar tendency. So due to the lateral structure of the jet, you see a spectral peak energy and luminosity that will decline with the viewing angle. So so considering the comparison with the observation, this is the comparison of a simulation result with the observed Yonetoku and Amati relations. With the point with the error bars is showing the observation data, and the color plots showing the three simulation results. And as you can see, all three models naturally reproduces the correlation curve. There seems to be some systematic offset toward higher energy for the Amati relation, but this may be simply due to the long injection duration imposed in our simulations, which is set by hand. So indeed, with the duration of the emission, which is close to 100 seconds found in the simulation, is in the rest frame is relatively long compared to typical long GRBs. So anyway, so the shorter injection duration is likely to reduce this tension. But anyway, the main message here is that although further confirmation is necessary, this is indicating that photospheric emission can naturally give rise to the Yonetoku and Amati relations. From the time resolved analysis of the emissions, we also find the Gornetsky relation is also naturally reproduced in the simulations, and these correlation results are broadly consistent with the independent simulation by Tyler, as presented in his talk yesterday. So this is giving further support for the photospheric scenario, but let me also mention on the shortcomings of our simulation. One of the main issues is on the spectral shapes. As mentioned earlier, the effect of geometrical effect broadening produces a non-total feature in the resulting spectrum. However, in most cases, it is not sufficient to reproduce the observed typical spectrum. So this is this pink histogram is showing the distribution of the alpha parameter of the time resolved analysis of a simulation spectrum, and the right is showing the beta parameter of the band function for the simulation, and with the gray on top of it is showing the observation. So as you can see, the simulation tends to show a harder value for the alpha and softer value for the beta, although there is some overlaps. So one possible possibility which may reduce this tension at some degree is one thing is to conduct a higher resolution simulation, which may give rise to further geometrically broadening effects. Or another possibility could be that this is indicating that some non-thermal particle arising from subphotospheric dissipation, which is not included in the hydrodynamic simulation, may be necessary to reduce this issue. However, this is just a discussion, and it's far from clear whether such effect is really will actually reduce the tension. And obviously, further study is necessary to pin down this issue. Okay, so next, let me mention the polarization signature. In our simulation, we also take into account the change of the polarization state due to scatterings, and these are the result of the degree of polarization as a function of viewing angle at a given energy band. So as you can see, polarization degree near the core region of the jet tends to be low, a few percent at the most. But as you go to larger viewing angle, when you start to see the wing region of the jet, the polarization degree tends to increase with the viewing angle, and it can be and also regarding the energy dependence, the higher energy tends to show higher polarization. So it can be as high as 30 or 40% at most at the highest energies. So our simulation predicts that the soft dimmer burst, which is observed at the large viewing angle, tends to have higher polarization. So although it is quite challenging to confirm such feature from the observation, in principle, these characteristics can be used to test this issue. So future missions such as POLAR-2 may provide some clues to this issue. Okay, so regarding the temporal behavior, we find a non-negligible change the polarization degree as well as the polarization angle with time. So this plot shows polarization degree as a function of observer time at the given viewing angle at the top, and at the lower part, I'm showing the polarization angle change with the observer time. The interesting feature find is that there is a not only the degree of polarization, but the angle changes with time, and the change in the polarization angle can be as large as 90 degrees. So this may be compatible with the those polarization angle change inferred in the previous polarization measurement. But one caution is that the polarization degree itself tends to be lower than those inferred in the observation. But anyway, at this point, the measurement itself suffers from the large uncertainty, so firm conclusion cannot be drawn at this point. Okay, so let me move on to the later part of the talk, which is on the short GRB simulations. So in this simulation, hydrodynamical setup is quite different from that of the long GRB simulations. Here we conduct a simulation starting from the vicinity of the black hole torus system in an environment which mimics the configurations after the binary neutron star merger. Here, it is assumed that the black hole is formed after 500 milliseconds after the coalescence of binary neutron stars. And as for the initial condition, we consider black hole torus system at the center, and at the larger distance scale, we consider ejector components, which is composed of the dynamical ejector and the hypermassive neutron star wind components. And given the initial conditions, we inject the jet at the from the inner boundary of the simulations with the parameter given like this. Okay, so this is the simulation of the this is the animation of the hydrodynamical simulation. One notable feature found in the current simulation is initially there is a quite strong interaction between the jet and the wind launched by the torus, accretion torus. And this strong interaction imprints a high time variability in the jet, and also provides a high collimation to the jet. After the initial strong interaction, the jet will break out to eject the components, and then eventually it will propagate to large distance up to the point it becomes optically thin to radiations. The simulations continues up to 4,000 seconds, but I will stop here. And so the resulting angular structure of the jet is similar to those found in the long GRB simulation, which is composed of fast-moving core surrounded by decaying wing regions. But however, the strong collimation force due to the torus wind results in turns out to produce a quite narrow opening angle of the core. In the current simulation, we find roughly 1 degree for the core angle, which is in contrast with the previous simulation, which do not consider the torus jet interactions. And this may be also in tension with the opening angle that is inferred in the observations. So the resulting light curves and spectra looks like this. This is showing the light curves and spectra for a given viewing angle. And interestingly, we find that there is a rapid time variability imprinted in the light curves, which is coming from the jet torus interactions. And this can be as short as 10 order of 10 milliseconds, and it can be compatible with the observed variabilities. The spectral shapes are, as in the long GRBs, spectral shapes are broader than the thermal shape, but still it is narrower than typical observations. We also find that the viewing angle dependence is similar with the long GRB case, which shows a sharp decline of spectral peak energy and luminosity at the beyond the core angle of the jet. So this is hence a correlation between the spectral peak energy, EISO, and the LP also arises in the short GRB simulation. However, while the correlation slope shows a good match with the observation, there is a offset from the distribution of short GRBs. So although it is not clear at this point, we speculate that this offset may be reduced by changing the simulation setup within a reasonable range. So maybe the narrow core angle that may contradict the observation may be maybe a key issue. So if we find a condition to reproduce by the jet, it may reduce the tension. But this will be tested in our future work. Okay, so this is a polarization signature, and it also shows the similar features found in the long GRB simulations. Near the core region of the jet, we find relatively low polarization, up to only a few %. But if you at the larger viewing angles, the polarization degree tends to increase, and it can be as it tends to be high at higher energy band, and can be high as 30 or 40% at most at the large viewing angle regions. So okay, so this is about all for my talk. So let me summarize my talk. From the simulations, we found that the structure developed during the propagation have a very strong impact on the resulting emissions. From the short GRB, which include the jet accretion torus component, we find that the jet torus interaction provides a very strong collimation to the jet, and also it imprints a rapid time variability on the emissions. We find that insensitive to the simulation setup, we always find a sharp decline of peak energy and luminosity at angles beyond the core angle of the jet, and which result in the correlation between the EP, EISO, and the LP. We find a very good match in the case of long GRB simulation with the observed Amati and unit correlations. On the other hand, we find the offset in the short GRB simulations. So we plan to test how such offset can be reduced by changing the simulation setup in the future studies. So as for the polarization, while the low polarization is found in the core part of the jet, it is found that it can be as larger beyond the core angle. So our simulation predicts that dim soft burst tends to show higher polarization, particularly at the high energy band, and in principle, it can be characteristics to test this scenario. Okay, so and one main shortcomings in the simulation is the tension found between the spectral shape of the simulations and the observations. While we find a substantial spectral broadening is produced due to geometrical effect in our simulation, it is not. In many cases, it is not sufficient to reproduce the typical observed values. So one direction to is that to perform a high resolution study to check whether resolution can change the situation, or another possibility is that maybe a population of non-thermal particles are necessary to produce the spectral broadening. But this is just a discussion. This should further. We definitely need updates in the simulation to pin down this issue. Okay, that's all. Thank you.
Yes, thank you very much for the very interesting talks. So we have some time for questions, like 5 minutes. So, okay, 3 questions. So Asaf, please go ahead.
Yeah, thank you for a very interesting talk. Did you try, I'm talking about the long GRB simulations. You said that you assume that the jet expands at the opening angle of 5 degrees, if I recall properly. Did you try other opening angles?
No. So we don't have we don't have such a simulation. So okay, yeah, that's Do you think it will change drastically?
Yeah, actually, I think it will change. I think it will change some things because of, like we saw yesterday in Orr's talk, I think some of the things we're seeing are due to instabilities that grow by the interaction of the jets with the surrounding star, basically the cocoon. And I think it might be sensitive to the opening angle. So I would recommend, maybe you can discuss later, I would recommend try a few of those.
I agree. Okay, thank you for the comments. Yeah.
Okay, there are 2 more questions. We'll start with Mukesh and then Orr. Please, Mukesh, go ahead.
Can you go to your first or second slide where you show the initial parameters, like the dependence of Lorentz vectors on theta and r?
Here, you mean? No.
The first or second slide of the presentation, where you show the dependence of. In the previous slide.
This one.
This one. You showed theta is proportional to, then r is proportional to, sorry, the Lorentz vector is proportional to r to the power lambda. So what was lambda assumed and
sorry, you're asking about this figure, right?
I'm asking about the values written above the top right of this cartoon.
I see. So sorry, so this is not my work. I just take this figure to kind of emphasize the non-uniform structure of the jet. Sorry, so I don't know. Don't remember the detail of this values. Sorry. Yeah.
What profile you assume then for Lorentz vectors?
For Lorentz vectors, so we assume initially 5, but it has a potential to increase to 500 in the terminal Lorentz vector. So such kind of parameter is assumed in this simulation.
Accelerating jet, is it?
Yes. Initially, yes.
All right.
And we have 1 more question from Orr. Please go ahead.
So actually, I have 2 regarding the opening angle. The first one is following a Asaf question. In long GRBs, if I understand correctly, you inject the jet manually, right, from the boundary conditions. So in a sense, you already set the opening angle, and this is tightly related to what you put by hand, what you get.
Yes.
Okay. So, and the other question is, in short GRBs, you say that it's further collimated by the torus.
Right. Yes.
From what I understand and what I see in simulations with jets with torus, the torus only collimates the jet initially, but after a while, the further collimation of the jet is achieved by the cocoon because the torus ends at some point. What I see in simulations is that the jet is starting to expand after the height of the torus. So if you can elaborate on this.
Yes, I agree with your what you said. But the fact that initially it is strongly collimated by the so after this initial collimation, it will eventually expand, as you said. But this initial interaction is actually kind of as far as I understand, this is kind of setting the initial opening angle of the expansion. So although we inject 10 degree of opening angle here, eventually when it escapes from the wind-torus interaction region, it will become quite narrow. So it will expand, but still it's narrower than the initial opening angle. So this is kind of computing the initial condition for the opening angle by the jet-torus interactions. So
I see.
Yeah.
Okay.
So
thank you.
Yeah. Well, we find that it's like 1/10 of the final opening angle will be 1/10 of the initial opening angle, which is kind of it's larger than what you find in your simulations.
So is it something that you looked into different opening angles that you set, and you find that it's always about 10% of this?
Good question. Actually, yes. So we did some. We are actually exploring on this issue, and actually it is quite so. Even if we enlarge the initial opening angle, actually it turned out to be insensitive to this initial opening angle. So it is kind of regulated by this jet-torus interactions.
I see. Do you have any plans of expanding this work to 3D as well? As Asaf mentioned, it's something that will affect the structure.
Yes. Yeah, I completely agree. I definitely agree. So we definitely need updates, and we want to do a 3D, but at this point, but we are planning to do 3D, but not in the near future, I think. Yeah, at this point.
Thank you.
Yeah.
We have one more short question by Tyler. Please go ahead.
Yeah, thank you, Hirotaka, for that really interesting talk. I just had a very quick question about your short gamma ray burst simulation here. You find in your light curve very, very short variability. And I was just wondering what the time resolution of your hydro simulation is.
Good question. So I don't have the number now, but I remember it's quite fine. So what we did is we step by step. So we increase the time interval of the simulation gradually with time, and actually we did a convergence check for this. So we kind of make it finer and finer and finer, and find at which point the result will converge, and this is the result we find at the final stage. So we at this point we think this is really the converged result.
Yeah. Okay. Great. I'm glad that you checked that.
Okay. I think it's time to go on the next talks. So thank you, Hirotaka, for the very interesting talks. Thank you for the questions as well. And
thank you very much.
So please, Yancy Mang, it's your turn. Go ahead.
Okay, can I start now?
Yes, absolutely.
Can you see my screen?
Yes, we can see your screen and hear you well. Please go ahead.
Okay, now I will start. Hello, everyone. My name is Yanzi Meng in Nanjing University of China. And today I will give a talk about the recent work on the photospheric emission spectrum. And my collaborators, including Bingming Zhang and Xuefeng Wu. And this is the outline of my work. Firstly, I will talk about the motivation, and then I will show the calculated probability photosphere spectrum for the impulsive traction and the more reasonable continuous wave. And then I will talk about the parameter dependence and the summary. Firstly, I will, in this slide that I will show that the gamma ray burst spectrum is quite diverse, but as we know that we can divide them into two categories. The first that's best fit by the Planck function and that best fit by the Power law. And with these observations, whether we can use the probability photosphere model to explain them is a very interesting question. This model is proposed by Asaf in 2008. And in my recent work, I just try to explain these two types of gamma ray bursts with this model. In these two published papers of mine, I find that the bursts that best fit by the empirical Power law can use this model to explain very well, whether it's the time integral spectrum or the timely sharp spectrum. In this work, for the short GRB 1708, which is the first burst that with joint detection of the gravitational wave and the GRB. We find that its maple spectrum, which is specified by the Power law, can be well fit by this probability photosphere model after reconsideration the off-acid emission from the subject. These off-acid properties is inferred from the gravitational wave and the librighting of the afterglows. And in this next work, we talk about the time-sharp spectrum. We find that using this model that the model predict or the theoretical predict spectrum evolution is quite consistent with the observations. We find that there may be two cases. If the jet isotropic is smaller, and the spectrum evolved from a Power law to this single Power law with negative index. And if the isotropic is wider, we find that the spectrum evolved from the Power law to another Power law, but the only difference is low energy index. Interesting, we find that these two theoretical predicted spectrum evolution consists with the 2 times the gamma ray burst. The upper panel shows the multiple gamma ray burst, and the bottom panel shows the single pulse burst. We find that they just correspond to these 2 times of evolutions. Also, after consider the initial acceleration radians to be much larger, just as these reduced values in Asaf's work in 2015, we find that the observed EP evolution of EP can be well reproduced. Just so in the left 2 panels, so what's next? Much work on the central engine models, whether it's the black hole or magneta, show that maybe the jet have 2 components, that it have a thermal component from the neutrino heating, and another component of the magnetic component from the Pauling flask. So if the jet is hybrid jet, what will we got for the photosphere spectrum? Interesting, we find that maybe after consideration, the hybrid jet and probability photosphere model, we may have the Banks time spectrum. Previous goals were have consideration the photosphere emission from the hybrid jet, but his work considered a fireball shock model, so it's quite different from our work. The basic theoretic condition of our work is quite similar to his work, but in our work, since we consider the probability photosphere model, so the photosphere spectrum is a multicolor black body, and in his work is the black body with a non-thermal component. So firstly, we consider the simple case of the impulse injection. See this figure, the red light, that we find that at later times, the power law that is much higher energy than the early black body just appears. So why this extra component exists? In this slide, we just place this simply. In this probability photosphere model, that when the precision is much larger than the photosphere radium, there's still a lot of photons to be to escape here, just so here, and from the equation here. So in this hybrid jet, since the existence of the magnetic component, that when we get the precision that much larger than the photosphere radiums, the magnetic component will still accelerate the jet. So the Doppler factor, the Lorentz factor will be much larger, and which means the Doppler factors will increase. So naturally, the observed temperature or the peak energy will be much higher. Then we consider the more reasonable of the continuous injection, that finally, after considering the structure, we got the realized and we find that for this model, the low energy index and the high energy index is quite consistent with the work, the observed typical values in each work. The parameters of the structure is just similar to our previous work. Note that from the statistical works that the bursts that best fit by the Bank function seems to be much harder. See the red circle is much harder than that best fit by the power law. The green circle. And so our model just naturally exploit this harness. Next, we try to discuss the maximum low energy spectrum index further. Just in Deng's work, he thinks that the maximum low energy index is 0.5. But in this work, with careful consideration, we find that actually the maximum alpha should be 0 and consist with this statistical result. This is because that in their work, they use the probability density distribution of beloved. So, but this distribution is quite well when the angle is much larger, but it's not quite well when the angle is almost equals to 0. See here the 3 lines. So we should use the other 3 probability density distribution, and we find that these other 3 distribution got the value of 0. So in total, that this model is for the low energy index distribution. So for this hybrid jet model, the parameter dependence is discussed as following: that is weakly depend on most of the parameters, such as the structure, the parameter of the structure, and the magnetization parameter. It only depends on the polar index of the magnetic acceleration here. In the previous results, we used the data to 1/3. It means that the magnetic acceleration is due to the reconnection. But if we consider that if the jet is initial as symmetric flow, it can be accelerated by the King instability. So the data can be larger, maybe a half. So consider these 2 accelerations, we got the data to be -4 to -3. And we find that it well consists with the better distribution for the smaller cluster in each work. So maybe this cluster for a special cluster of gamma bursts may be produced by the hybrid jet in the Photospheric model. Here, I give a brief summary that within the probability Photospheric model, if the jet is a magnetic jet, maybe it well consists with the bursts that best fit by the polar model. And if the jet is the hybrid jet, the spectrum is quite consists with the spectrum for the bursts that are the best fit by the bank function. Thank you.
Okay, thank you very much for the very nice talk. So guys, do you have questions? There is a question. So there is a question by Chandra Bahadur 6. How is kink instability possible in axisymmetric flow? It is realized only in 3D setup.
I'm not really quite clear. Can you repeat that?
It is written in the chat. I repeat. How is kink instability possible in axisymmetric flows? It is really realized only in 3D setup.
This is naturally when the jet that inject from the neutrinos, they are or if the rotation axis is different from the magnetic axis, it is normally accelerated by the connection. But if the jet is the rotation axis is arrived with the magnetic axis, just as show that is an axisymmetric flow, is quite possible that is the acceleration is due to the kink instability.
Okay, does that answer your question? I actually do not see you in the participant list, so okay, let's hope it did answer his question. Does somebody else has a question? No, so if there is no more questions, then we'll go on to the next speaker. So the next speaker is Michael Burgess. So please share your screen and go ahead.
Okay, hello.
Yeah, we can hear you and see your presentation.
Awesome. Okay, so hi, I'm Michael. I'm going to invade the photosphere session a bit to talk about synchrotron and photosphere, and also how to fit GRB spectra and some of the things we need to worry about and kind of where we are right now with the situation. So if you take anything away from my talk today, it's mostly to stop using the band function, alpha, and any correlations derived from them for physics, because they're not going to give you the correct answer. And if you base your theoretical models on trying to reproduce things like the alpha distribution, etc., you might run into some issues when we start really fitting all the physical models in the future. And also I want to dispel 3 myths that there's this thing called the line of death, that spectra are narrow, and that there is millisecond variability observed in GRBs. So let's start out with what are the data. This is a typical, in the data space of GBM, this is what our count spectra look like. The Poisson distributed counts as a function of channel energy, not real energy. And how can we use this to understand what's going on physically in a GRB spectrum? Well, here's our band function. You notice it doesn't look anything like that. Of course, one is in nu space, the other one is in normal photon count space. The way we understand this is by folding the spectrum through this highly singular response matrix. And by highly singular, I mean we can go one way and we can see what the spectrum looks like next to the data, but we cannot go back the other way. That's why we have to do forward folding. And because of this non-singularity in this matrix, you can have 2 solutions to this equation that look very similar in the data. These 2 different, can you see my mouse? These
yes,
2 different,
yes.
Thank you. Yeah. These 2 different spectra look very similar in the data, even though they would look very different in nu. So if we start trying to do modeling on this nu space, or with empirical models or some kind of empirical measures to determine what's going on in physics, we might get the wrong answer. And so we'll start out with something that I think we're all familiar with, the line of death. We've been fitting this band function to GRB spectra for a long time. We concentrate mostly on alpha, although there's other important things. And we look at this catalog distribution of alpha values. And the basic idea is if you're on one side of the alpha distribution, maybe it's optically thin emission from something like synchrotron. If you're on the other side, okay, maybe it's some sort of thermal emission like sub-photospheric dissipation or non-dissipated photosphere emission. And that's been the story for a long time. But then when people started fitting physical models of synchrotron to data, like even in 2015, the GBM team and myself in 2014, we saw that we could actually fit synchrotron even to spectra where the low energy index would rule it out. We got hints. So this means that, okay, maybe we need to find another way to use the band function to do physics. Following that, some people had the idea that instead of using just the low energy index, you could instead use the width of a band function fit. And there are 2 different ways to do this. 2 different teams came up with this independently. You can use the spectral width as an angle, or just the width, it's kind of like the full width half max thing. And the idea was this. A black body or thermal emission is going to be very narrow, and synchrotron is a rather broad emission spectrum. And so if you can derive a distribution of widths very similar to the distribution of alphas from the fits, then you can kind of distinguish between thermal and non-thermal emission or synchrotron emission naturally. And so people did this, and they found out that, once again, synchrotron seems to not be able to reproduce the spectrum, or is not responsible for the spectrum that we see. So I thought this was very interesting. So I took some of these spectra and I fit them with synchrotron. So these are 2 fits to GBM spectra with a very simple synchrotron model, slow cooled. There's no evolution of the electron distribution or anything, fit to normal GBM data. And if we take these width distributions, we can divide, we can make this plane from the 2 different width distributions in the gray areas where synchrotron would be projected. So after fitting several GBM spectra, we found these circles with their color being how good the fit is, yellow being kind of bad, black being kind of being a good fit. These were up in the region where synchrotron wouldn't be rejected. Cool. And then of course we found some spectra that were not good fits to synchrotron, and they kind of span the whole distribution. Then we looked, there's actually a lot of spectra that were even down in this deeply rejected regime. In fact, these two spectra that I'm showing you here are down in that regime. And that means that, okay, also maybe this width empirical measure is not a good way to distinguish spectrum. But how distinguish emission levels? But how do we? Why is this? Well, it's basically this thing that I was showing you earlier, is that you can have two very different spectra in photon space that look very similar in the data. And so if you try to draw conclusions from here instead of from here, you might get to the wrong answer. Yeah. So what do? Let's fit physical models directly to the data. So building upon a lot of the work that has been going on with fitting very steady state synchrotron models, very simplistic synchrotron models or functions, whatever you want to call them, Damien and I sat down and we made very fast code that solved the cooling equations for the electrons, only assuming synchrotron emission. So we inject a power law of electrons, we let them cool, and as we cool, we integrate over their emission, and that gives us synchrotron emission. So this kind of looks like this, and what I want you to understand from this movie is we're not fitting the band function, we're not fitting just broken power laws or empirical things, we're actually fitting this spectral function that can evolve through all these different shapes directly to the data. How do we do that? We have to use proper statistics. So I know this is mostly theory here, but if you see GRB analysis with GBM or XRT or whatnot that uses chi-square statistics or something, you should ignore it because it's improper, and the model, you may be able to minimize on the data, but the conclusions and model comparisons that will be derived later will be incorrect. I won't go into too much detail about this, but just pay attention to that. Now, using proper statistics in this model or function, this is what we get. We fit 18 GRBs, 168 time resolved spectra. We chose GRBs with single pulses and redshifts so that we could later derive some physics. And this is an example of time slices through one of these GRBs. And so this is the data space. This is the fitted model folded through the GBM response, the BGO response, the LAT LLE response. This is in photon space, the uncertainty on the nu spectrum. These are the distributions of the cooling frequency and of the injection frequency. And by folding our posterior back into our simulation, you can actually look at the distribution of the electrons that would be emitting at these different time slices. So you see slow cooled, moderately slow cooled, and very fast cooled in these three different time slices. And we found this, and this is another example of a GRB with LAT data, kind of the same similar behavior. How do we know that these were good fits? So out of those 168 spectra, we rejected 3 that were that seemed to have problems consistently in several different detectors. The way we check these fits is by doing something called posterior predictive checks. And posterior predictive checks, what this here is, this is called the posterior predictive distribution. It's the probability of future data given the observed data. And it's an integral over the future data the future data's likelihood conditioned on your fitted posterior. This is a very complicated integral to solve, so we do it by Monte Carlo. We take our posterior that we got from conditioning on the data, fitting, and then we generated new data with the Poisson likelihood, and that's how we arrive at this distribution. And the idea here is that the future data from the model that we fit should look like the data that we observed. And one way to look at this is like this. So this is an example of a fit to a GBM spectra, 3 different detectors. The observed data are in yellow, and the replicated data, this posterior predictive distribution, are these gray shaded regions here. Of course, this looks very, you have to go through a lot of these fits, so this may not be the best way to go through by eye and say, okay, these fits look good. You can use what are called QQ plots and integrate along the observed net counts, so background subtracted, but not background subtracted in the fit, and the predicted counts from the model. And the idea is that these regions should lie on a one-to-one correspondence. In other words, that the model is predicting the data that we saw. Oh, oops. And so we can see a bad fit when you get a deviation from this, and this is what these kind of look like even when you simulate and fit the true model that you get. So that's how we ran through and checked that all the fits were working. And since we felt very comfortable that most of the fits, except for a few, were working, we went through and did some physics with the fits that did work. And so out of these 18 GRBs, we can look at the distribution of the cooling, gamma cool over gamma injected in our model. So it should be gamma cool there. And these are the distributions that we infer for that. And so if you're on this side of the line, or in this gray region, you're in the fast cooling regime. If you're in this region, you're in the slow cooling regime. And as you can see, there's kind of a mixture, but it's mostly in this moderately fast cooling or slow cool regime. So that's what the data give us. And there's, yeah, if you fit this type of synchrotron function to the data, this is the answer that you get. The really interesting thing is coming back to what happens with the band function is we went back and fit all of these spectra with the band function, and we compared what the cooling regime was to the alpha distribution. So this blue would be very slow cooled, the red would be very fast cooled. And you do see that this kind of mimics what we expect from the band function, right? So you'll get steeper alpha for fast cooled spectra and harder alpha for slow cooled spectra. You can see we're sort of violating the line of death here. And even in this regime where we really wouldn't expect to be able to fit synchrotron spectra, we get alphas that would strongly violate the line of death. And once again, we're back to this thing that one thing, there's a lot of curvature in the synchrotron spectra, more than what we think, more than just these asymptotic regimes that are typically quoted. But energy dispersion is kind of playing with us again. So these are two of the spectra with very hard alpha. This is the band function fit to that spectrum, and this is the synchrotron fit. Both of these are good fits to the data, but you get very different spectra, very different results depending on what you assume. And it's back to the same problem again that we were discussing earlier. Models can look very different in new space, but look pretty much the same because of energy dispersion of the detectors in the data space. And we kind of knew this. Back in 2015, we did a little study where we treated the entire GVM catalog like it was coming from a very simple slow cooled, a very simple fast cooled synchrotron model function. And we simulated those spectra, fit them with the band function. And we saw that as EP decreased, you would measure different alphas than what you would expect from theoretical predictions. So kind of know these things, that the energy window, energy dispersion, everything was going to screw up things if you use the band function. So if we, under the assumption, we're not saying that synchrotron is the best model, the correct model or anything, but if we fit that model, we can now try to do some physics. Unfortunately, the way that we did fitting, we have to assume things like the radius of the emission, the Lorentz factor, we have to put those in, and then we can take the posteriors of our fit and start computing physical parameters. So Damien sat down in a beer garden a few summers ago and derived some really cool ideas where we could compute a lower limit from pair-opacity, so the high energy emission of the bulk Lorentz factor. And you can also, since we don't fit or find a thermal component in the photosphere, we can compute an upper limit from the lack of a photosphere. And we conservatively assume that there could actually be a subdominant photospheric component that we don't see at 50% of the energy flux. So we can fold our fits through these, the posteriors through these two things, and we can derive where these upper limits would lie. So our upper and lower limits. So the compactness lower limit, these are the lower limit from compactness, and these are the upper limits from the photospheric emission. And obviously they're inconsistent with each other. And that means that if the emission is synchrotron, what we're from these fits, then the fireball model can't really work in that case. If that's true, then we need to invoke magnetization. And so Damien sat down and did some more calculations, and by assuming different inputs, for example, the level of magnetization and the co-moving Lorentz factor, he did a little like mini jet model. We could compute things like what, as a function of, for each of the fits, what is the bulk Lorentz factor in these different regimes. And you can see here the posteriors, they're colored for their cooling regime. We can also compute the radius of emission. Unfortunately, or I'm not sure if it's unfortunately, these computations without a lot of magnetization and some a co-moving Lorentz factor, so some sort of mini jet, you get radii that are quite hot. So the jets have to be at least moderately magnetized and something going on with to deal with the variability timescale to get radii that are what we would expect from some kind of model. So that is what the observations when you fit with synchrotron tell us. Okay, what about variability? Well, yeah, if you have very fast variability, high radii don't make a lot of sense, but very fast variability doesn't really exist in GRBs. So there's this study by Gokul et al. In 2014, 2015. They did a study of Swift and GBM GRBs, and they computed the minimum timescale variability. As you can see, millisecond time variability is a very rare feature in GRBs. So most of them have maybe, I don't know what the average is here, but sub-second to second variability. Maybe there's some that they did a sensitivity analysis to see how low they could go, and I think this is what this. The details are discussed in the paper, but in general, they think this is where the variability is. So if you're wanting to propose a model with millisecond time variability and say, okay, well, you can't have these high radii, you've got to now figure out where's the millisecond time variability of gamma ray burst. Okay, oops. Yeah, so what about photospheric emission? So then there was a nice study done in 2019 by Bjorn Algren, and they went and fit a subphotospheric dissipation model to a sample of GRBs, one of them coinciding with one of the ones from our sample. And I think it's the model developed by SF. And they found that you could fit regions of gamma ray burst in some time intervals with a subphotospheric dissipation, but these red regions here are where the model fell, even though we could fit the entire region, the entire time result spectroscopy of this GRB. So here we actually are starting it to where instead of comparing different alphas, we're starting to compare different models and seeing which one fits the data better. So it's, for example, in this one, where the GRB is very bright, subphotospheric dissipation didn't seem to fit the data. This is a subset of subphotospheric dissipation, so maybe modifying some of those parameters will get different results. But we do see in that study that in general, when the GRB is very bright, the model doesn't work. So perhaps there needs to be more efficiency in the model, something like that. But then you start running into efficiency problems like you have with the synchrotron emission. More recently, there was a study of non-dissipative photospheres, which SF spoke a lot about yesterday. And they actually, we can call this a physical model because they derived an empirical function that modeled this physical model. And in the study by Knur et al. In 2019, they fit this spectral function to some data from the David Yu et al. Time result catalog. But the claim that a quarter of GRBs could be coming from this model needs to be tested. Because in that study, what they did was they analyzed a single time interval in a set of GRBs, and that single time interval corresponded to the spectrum when fit with a cutoff power law, had the hardest alpha. Okay, so what does that mean? So let's just go ahead and repeat that. And then they also, in that study, fit a simpler synchrotron model and did model comparison between them. So we took one of these GRBs, GRB 17, 01, 14, 19, 17, and we first fit with the band function and determine the alphas. Now we get a different alpha with the same data, same time intervals than they did, but this was the interval they claimed had the hardest alpha. This was their value, this is ours. So let's fit this non-dissipative photosphere model and our synchrotron model, and let's look at what happens. Well, you can see here the non-dissipative photosphere model in the stream is actually failing on the data. So is a synchrotron. So if we do model comparison between these, it doesn't really mean anything because both of them are failing to fit the data. As you see in a good fit, you get this really nice one-to-one relation. So in probability theory, you can't use marginal likelihoods if your fit fails. It will give you meaningless results, and for lots of reasons. We can discuss about that later because I'm running out of time. But then we can go and look at, instead of just the hardest alpha spectra, we can look at the entire burst. We can fit it with this non-dissipated photosphere model, and we can see this model is not really doing well around the peak. And sometimes the synchrotron doesn't do well right here around 10 keV, where we don't have good calibration of our response. But in general, the synchrotron model is doing well. And if we look at a movie of all the spectra played time to time, you see the synchrotron model is doing okay through most of this burst, but the non-dissipated photosphere model basically misses the curvature of the peak a lot of the time. So we need to be careful with the claims about that 1/4 of GRBs can be fit with this model at the moment. Also, we fit this GRB, but this GRB was observed by Polar. We found moderate polarization in this. I don't have time to talk about that, but Merlin will talk about it in his talk tomorrow. Yeah, I will. Where our former PhD student is working on some photospheric models. Current PhD student is doing some really nice stuff with integral SPI, fitting synchrotron models with high resolution to determine the cooling frequency better. I'm currently working with Savaki, Sironi, and Belobordov on a new synchrotron model to fit to the data. And just want to wrap up. Let's stop using the band function. And if you have a physical model, let's fold it through the response and fit it to the observed data. So thank you.
Okay, thank you, Michael, for this talk. Very much data oriented. So it's good after all the theory and the simulations. So do you have questions? Yes, Gregory, you have a question. I see you raise your hands. Go ahead.
By the way, how much time we have for questions for this talk? I guess we can run for a long time. Anyway, it was really a good talk, Michael. I have really one comment, one question. Comment is somewhat simple based on our experience in different fields. You know, this battle between photosphere and synchrotron as a radiation mechanism reminds me somehow of a much more fierce battle between loop quantum gravity and string theories, which ran for years, decades actually. And the outcome of that is actually that people seem to be appearing to converge to somewhat same conclusions from completely different fields. So could probably this happen also in our field? The time will show. This is a comment, but let me tell you, really ask you a question. Going to physical origin of the soft spectra from synchrotron, is there any idea where this soft low energy spectra come from synchrotron? In other words, the line of death argument, what's wrong with it?
Well, the line of death argument is because the band function can fit the data, but GRBs don't emit band functions. So you're fitting with a function, and then you try to derive some asymptotic limit and then compare it to a theory. But you can then take that same the actual physical function from that theory and fit it to the data, and you get two different answers. It's just because of this energy dispersion. So if you want to rule out synchrotron, fit synchrotron and show that it doesn't fit the data. Same thing for the photospheric models. I mean, I don't think there's a battle between these. I think the difference is that it's very difficult to compute these numerically and fit them to the data. And so the more of these that become available, publicly available for us to, observers to fit them to the data, the sooner we'll start to learn what's really going on. But right now, there's actually, it's very difficult. There are very many models that are publicly available.
There's a question by Bin Binzang. Please go ahead.
Oh, hi, Michael. Yeah, nice talk. We talk about synchrotron live. Which synchrotron talking about? I mean, we have a bunch of electrons, and you have to assume a distribution of that. Are you talking about single temperature synchrotron, or synchrotron with broken polar, diffused, or cut-off polar, or whatever?
Yeah, I mean,
right?
Right. So yeah. So in our model, it's just we just inject a single power law of electrons. Like in your model, you also inject a single power law, but you have the magnetic field decreasing with time when you solve the equation. So you basically you have fast cooling at the very beginning and then more slow cooling at the end. And I think we both get, because we both get basically the same kind of results.
Yeah.
So I think we need more predictive. We can basically fit the shape to the data. We need some predictions about the jet geometry, the dynamics, stuff like this that give the results, that give more predictive results.
Yeah. Do you think the data currently can distinguish that the different electron distributions?
Yes, but yes. I can't say more until maybe next year. I think, yeah.
Okay. Okay. Thank you for the answer.
There's one more question. Asaf, please.
Yeah, it's more like a comment. I think that your main mistake is that you're only taking one ingredient, which is the radiative process. And the question that you ask then is which radiative process under certain conditions, or let's say more precise, under the best conditions would be the best fit to the data. While as we know, life is not so easy, and there is not just the radiative process. There is a dynamics, there is some complicated progenitor, which we're not really certain about the entire, emissivity profile of the progenitor. So I think that the correct answer would be, the correct question to ask would be, which model, and I'm talking about the model, not about the radiative process, is mostly consistent with the data. Does not have to be the best fitted with the data for a single burst or for a small sample of bursts, which we can discuss about later. And I think that when you look at that in this direction, then you find out that the photospheric model is by far, as a model, more completely fitting the data than the synchrotron radiative process. Although I agree with your assessment that in many cases, just based on the low energy spectral slope is not sufficient to rule out the synchrotron as a radiative model. But this is just not radiative model, sorry, as a radiative process. But this should be taken only as one ingredient of an entire model, which includes the dynamics, includes the inner engine, including the jet structure, many other things which I discussed yesterday.
But this doesn't exist for the photospheric models. I mean, you just...
Of course it exists.
Well, then what's the spectral evolution for photospheric model? Because we have this power law evolution of ET, but there are no predictions for that yet.
No, we discussed about it yesterday. There is an evolution of EPIC, which there is some predictions for the photospheric model. I am willing to agree that it's incomplete, and there is more room to continue with working on that. But that does not mean it does not provide any information about it.
Sure. I mean, I only know how to compare it to data. And at the moment, I haven't seen convincing evidence that photospheric models can fit the data consistently in a large sample. And indeed, synchrotron can't also fit all of the GRBs, but it seemed to be consistent with, at least without making any kind of special cuts, except for we look at GRBs with single peaks so that we make sure we don't have overlapping emission. We look at GRBs with redshifts so we can go back and try to at least compute some of the physical parameters. For example, these plots here are sort of what you're asking, right? Like if this is the emission model, what radii would the emission come out with? Now, we may not like the answer, right? It's very high, but there's not much more physics. I mean, there is more physics you can do, but this is pretty macroscopically the answer that you get, unless I'm missing something.
It's not whether I like the answer or not. It's whether the answer is consistent with what we know. Basically, what you're saying, I need to get something that have about Lorentz factor of a few hundreds, or maybe even up to 1,000 or more, to radius of 10 to the 17 centimeters. And then the question that is being asked is whether this is physically possible or not. Right, and I don't know of anything that can do that. Maybe there are things which we don't know of. I agree. This is not necessarily the fact that I don't know it does not mean it does not exist. But the question is, do we have any evidence from data, which is not necessarily from GRB data, right? For example, do you have any evidence from measurements of the interstellar medium that can support or rule out such a scenario? And I think the answer is yes. We do have some evidence of what should be, what is the densities that we know of the interstellar medium. We do have strict physical constraints on what is the energy that can be released. So we cannot just say, okay, well, there may be some model which can give you Lorentz factors of 1,000 at radius of 10 to 17, while we know that this is physically impossible, based on measurements of data that we know, measurements of interstellar medium density that we know of. It's not just because I don't like the number. Right? It's not about liking or not. Right? It's about what we know.
Yeah, I mean, if there aren't models that can reproduce this, then these results are a problem.
On the other hand, people have already put explanations as to how to try to explain those, right?
Yeah.
I mean, Ghiserini, for instance, is trying to do that with proton synchrotron. It has also its load of troubles and problems, but somehow, if nobody had looked in that direction, those ideas would not have emerged.
Yeah, that's why I'm saying that I think the correct question should be not what model best fit the data, but whether the outcome of a model is consistent with the data.
But somehow you cannot ignore the spectral fitting. I mean, your model can very well reproduce epoch and luminosity and variability, but if it fails at explaining alpha,
of course,
then you are running into the same kind of problem somehow.
I fully agree. A model has to be consistent with all the data, not with part of the data. If a model is only consistent with part of the data, but not all of it, it is an incorrect model. There is no question here.
The discussion is very nice, and I would propose everyone to postpone possibly this discussion if we have some time left at the end of the session. Probably we can go on with the other talks.
Thank you.
If you don't mind.
Thank you.
We are a little bit in advance. Maybe it is worth taking 5 minutes break before starting.
As you prefer, but since we have quite still a number of speakers, it would be nice just to go on and eventually have little time for discussion at the end.
Yeah. Okay. So then let's proceed. So Liang, are you here? You're the next speaker.
Hello, Damin.
Hi, Liang.
Hello,
please go ahead, share your screen.
Hello, can you hear me?
Yes, we can hear you well.
Okay. Sorry. Can I start? I mean.
Yes, of course. Yes.
Can you see my screen?
No, we cannot. You're not showing your screen yet.
Now it is okay?
No, still not.
Okay, sorry. Within minutes, I ask correctly, okay?
Probably there is some information.
What's going on?
We are waiting. I don't know. He apparently disappeared. Or let's wait for one more minute. Gregory, are you here? No, he's not here too. Okay, let's just wait for 1 minute, and if not, then we can exchange Liang and the next speaker. Okay.
Allow
Okay.
sharing. It didn't allow sharing. Doesn't work.
This disappeared.
No, this nothing to do. Setting, try setting. I don't know what was the problem with the screen sharing. There's no button. Can you hear us?
Yes, we can. We can.
There is no button for screen sharing in Mac. I never,
No, I think Photospheric has no this function, but change to
anybody
natural, like for Chrome.
Anybody can help?
I can't.
Yeah.
Don't use Safari. Use Chrome. Google Chrome.
Chrome. Use Chrome. You got it?
Yes, yes, I use
this Chrome. Is this Chrome?
Yes.
Let me see from our side, but it looks strange.
Okay, if it's not working, Liang, can you arrange to have the presentation sent to another computer?
Does it work? No?
No.
Doesn't?
Still not.
Where is your presentation? You can show it from my computer.
Eventually, we can invert the speakers the time you sort this out.
Wait a second. You have it on USB then, or you can send it by mail?
Or I send to you by Skype.
Just send me. What's Skype?
Okay.
He can eventually present from my computer if you don't mind. Let's see if it would work. Just a second.
Well, it worked yesterday. So there's no reason it doesn't work today.
Since we have some time, fortunately, gained. Okay.
We are running out of time now. Now we are dead.
No, don't worry.
Timing.
Okay, here we are. Okay. Let's see if I can share my screen here. Can you see it?
Yes.
Okay, then you like to go, to run from your computer, or I can just change slide for you if you prefer. Okay.
Yeah.
Okay. Just tell me.
Okay.
When to do that. Okay.
Okay. So okay, you can change it for me. Okay.
Yeah.
Gregory. Thank you.
Sorry. Yeah. Okay.
Okay.
You can start.
Hello, Dami and everyone. I just listened to Mike's talks and what can I say. Today we're going to talk about the basin time resolution spectroscopy of multiple cells gamma ray bursts detected by FEMI, and variation of the emission property among pulsars. My collaborators, including Felix, Asaf, David, and Jolim. Gregory likes. And all my today all my talk is based on our recently paper published on IPGS of likes. Okay, this is my outline. First, I will talk about our motivations, and then to introduce our sample selection and the data analysis. Then the observations, probabilities among process, and then the assessment of the compatibility with the emission models, and the last is the discussion and summarize. So our motivation is we want to use the FIMB multi-process force to investigate the observation and the emission properties among the process within a burst. The observation properties including like the parameter distributions.
Ask Gabriele, I'm changing slides for participant. I'm sorry.
Gregory, you should mute yourself, please.
Okay.
Go ahead, Liang.
Gregory likes.
Maybe you go to Gregory's desk and you speak from there.
Oh, okay, sorry.
This is the simplest thing to do, I think. Liang, we cannot hear you. Liang, we cannot hear you. You are muted. Liang, you are muted. Okay, I don't know what we should do. Yuan, are you in ICRANet? Can you go there?
I'm not there, but that means you are the host. You can unmute it.
I cannot unmute Gregory. I asked it to unmute him, and I asked him to start the video.
I'm in China now. I'm not in.
Yes, right. Sorry, I forgot about it. Right. Liang, we cannot hear you. I don't know. Let me try something else. That's working.
Hello, Damien.
Yes, Liang, we could not hear you.
Yes, because sorry, because I just use the Gregory computer, but I cannot.
Yeah, but Gregory is muted. Can you just unmute yourself and use Gregory's computer and start over with your presentation?
Yes, I have used the Gregory computer, but I cannot.
But Gregory is muted. Can you unmute Gregory, please? Gregory's sound is muted, so we cannot hear you when you're there. Can you just unmute Gregory's?
We can talk later, okay?
All right, you do the next talk or the one after. So all right. Let's do like this. Now mute yourself. I will mute you. It's better. Okay. Yes. And you need to stop sharing Gregory's thing. Gregory's desktop. Liang, you need to go and stop screen sharing. Come on. Liang?
Yes.
You need to go to Gregory's computer and you need to stop screen sharing. So this is exactly why we actually gave 30 minutes in advance for people to connect and check that their system was working. So if you have to speak in other sessions, please do so. There was actually 2 persons today, but at least it was working. Liang actually completely left, or is it me? All right, let me try something else. Okay. Okay, I don't know. We are blocked. I cannot ask him to remove his screen sharing.
Damien, if you're host, I think you can actually stop the screen sharing.
I don't know how to do that, right?
I don't know how either.
How do I do this? Like this, maybe. This will stop other screen sharing. Yeah, oh yeah, I can do that. Okay, so I guess now you see my screen. No, I stop. Oh, okay, perfect. I managed to stop. Okay, so we will resume with them later when they manage to solve their issues. And so the next speaker is actually Hisne Dereli. So she will speak about classifying photospheric emission in GRBs. So yeah, please share your screen and let's start. You need to put yourself in full screen.
Yes. So, hello everybody. Can you hear me?
Yes, we can.
Okay. Yeah. First of all, I would like to thank for giving me opportunity to speak in this session. So this is the title of my presentation. It's the classification of photospheric emission in short GRBs. This work done with the collaboration of Asaf Pear and Felix Wright. So I want to take a reference of previous talks and also the talk given by Asaf Pear on Monday. And I want to say that the expected spectrum from photospheric emission is the pure Planck function. And if you consider the geometrical effect, you can have broader functions in the energy spectra that like here you see the red one, it is the photospheric emission from acceleration phase. And here you see the black line, it is the photospheric emission in the coasting phase. And you can also, there is an estimate of the low energy spectral index by Belobodorov, and they estimate that this spectral index should be around 0.4. And then there is the expected photospheric flux from the GBM. But this has 2 limitations. The first one is the limited bandwidth of the GBM, that the estimate of the low energy slope is not correct in low energies. Or the second limitation is the cutoff power law function using the empirical function that you can see here in the photon spectra, the photospheric emission model and the cutoff power law model is in blue overlaid, and low and at low energies, the cutoff power law estimates the softer spectra. So there are two ways to overcome such a limitation. The first one, that you can use the theoretical model and fit the data directly. You will see this in the next talk given by Björn Aldren. And here in my talk, I will concentrate on the method that you can also use theory and the empirical models. How we do it, we take the spectrum, expected spectra from the theoretical model. We consider the response function of the detector, and we simulate the synthetic spectra, and we fit this synthetic spectra with the empirical models. Here we use the cutoff power law model, and actually this work done by Ajiner. And here in the figure, you see that the alpha, it is the low energy spectral index and peak energy. And here, these data points, the blue ones that you see, is obtained in the range of the energy range of the 8 to the 2000 keV with the signal to noise ratio 20. And these green data points are obtained with the signal to noise ratio 30. Here you also see the blue lines that are obtained when you give a limit, when you limit the energy, and you can get such a line also. But my reference line will be the one that I obtained with the signal to noise ratio 300. So before doing that, I want to say how we select the sources and our analysis method. So we use the single pulse burst sample detected by the Fermi GBM. They are short GRBs. Definition of the short GRBs is that the T90 smaller than 2 seconds. So we apply the Bayesian analysis. We use the empirical model cutoff power law, and we made the time resolved analysis. And we select the bins that have a significant larger than 15. And we assume that the single emission is responsible from the whole duration of the pulses. And here you can see the distribution of the alpha. We select the hardest alpha, which is generally close to the peak of the pulse. So then for each sources, we get this hardest alpha, and we plot the distribution of this hardest alpha. And we saw that the majority of this hardest alpha obtained from each pulse is incompatible with the synchrotron line of Dart. And this is 70% of the source. And we compare this, that is with the long GRBs, that the hardest alpha also obtained from the single pulsed long GRBs. This is 60%. And we also compare previous study. However, in this work, they include all the time resolved spectra, so that their fraction is 28. And ours is much larger than this. So we put this hardest alpha versus the peak energy, and this line that it is from the non-distributed photospheric emission model with the synthetic data. And I also want to outline here that this data that we obtain, the softest value that you can get from single pulse with the bin, it's around minus 1.25. And here you see that the source that has several peaks, several bins, that is very bright. But my point is that here you see the green dots, they are compatible with the non-dissipative photospheric model. And this is like somehow the single origin. It is the clue for a single origin, that the two pulses they have a two pulse in their light curve, this source. Two pulses originate from the non-dissipative photospheric model. However, you see here with the blue dots that the first peak is compatible with the non-dissipative photospheric model, and the second peak is most likely another emission like synchrotron. So, and when we check this sample, which are compatible with the photospheric emission, we find that the fraction is 1/3 of the sample, like 35 of them is compatible with the poor thermal emission. And we compare this with the one obtained from the long GRBs, it is larger. And if we compare this fraction with the will to push long GRBs, you will see from the talk of Liang, this fraction in the first peak is larger, and in the other peaks, the fraction is decreasing. Here in my study is the most important result that when we compute the Lorentz factor for those GRBs compatible with the poor photospheric emission in a constant place, we find that here you see the for the short GRBs is the gray. We find two peaks. And when we compare this with the long GRBs, we didn't see this. And so we find a bimodal distribution for those GRBs in the Lorentz factor. And when we check this in the hardness ratio, we also find bimodal distribution. As you can see, is the first peak is lying here and the second peak is lying above. So we think that this first peak is the intrinsically short GRB population, and the second peak is somehow is the tail of the long GRBs. So we also made the parameter correlation check for those sample above the enthalpy line, and we find that there is a correlation between the T90 and the peak energy. As you can see here, the mean of the posterior distribution is 0.5, and you can see here the spread of the posterior distribution for this correlation. And however, we didn't find any correlation in the flux, and we conclude that the similar amount of energy released in the short GRBs, which lead to high temperature. So this gives some clue for the understanding of the progenitor model or the explosion mechanism of the short GRBs. So to conclude my talk, I want to point that it's important to make a time-resolved analysis and select the significance, the bin which has significance larger than 15. And in our work, we find that the larger amount of the short GRBs are consistent with the poor thermal origin. And this is, we also checked that maybe another larger fraction can be the thermal origin, but at later times they are contaminated with the other emission mechanisms. So as a result, the thermal emission very common between the short GRBs. And when you consider the non-dissipative photospheric model, and you can find two kinds of short GRBs. So the T90 is not the restrict criteria, and we can we can separate this restriction with our model as well. So this is the end of my talk. Thank you so much. It was, and I will be happy to have questions if you have.
Thank you, Husna. Any question, please? We have quite a lot of time for questions, for any comments, questions from the audience.
What is happening?
No, it's okay. You were muted apparently.
Yeah, I was muted, but since you took over speaking, so I let you speak. Okay, sorry. Okay, so let's go for the next speaker. Is there no questions?
Yeah.
So should we make Liang again, or should we? Liang is not here actually. I don't.
But I didn't get. He made the talk or not? After all.
He went through one slide and then you left and then started the mess.
Oh, I see.
So I basically told him to go to your.
Yes, and I left him here in my room, thinking that he is presenting. Anyway. So Husna was speaking instead of Lilian. Let's see. So we can pass to the next speaker possibly, and then try with Lilian if necessary.
Okay, so then it's Bjorn. Bjorn, you told me that you are here, right? That you are ready.
Yes, I am.
Excellent. So yes, please then go ahead.
Yes. Let me just. There we go, and screen sharing. Oh, I got a virtual background. Yes, there we are. Can you see my
yes, absolutely.
Slides? Great. And you can hear me as well, it sounds like. Great. So, hi everyone. I'd like to start by thanking the conference organizers for the invitation to speak. It's been a really nice session, and I look forward to the ensuing discussion and the rest of the conference as well. So in this presentation, I'm going to show results from a work published in 2019 of a study of joint Fermi GBM and Swift XRT observations using a model for subphotospheric dissipation. And in the context of this work, I'm going to talk about why we fit physical models and reflect about what we can learn from the fitting of physical models directly, and talk some about fitting photospheric models in general. So, I mean, at this point, we don't really need an introduction, but the 10-second plug would be, we want to understand prompt emission. And this is often done by analyzing spectra. And spectra are often analyzed using empirical functions like the band function. This feels fairly well established at this point in the session. Now, the problem, obviously, being that physics is not generally reliably inferred from empirical models, the band function included. So let me substantiate that claim a little bit. Now, Michael already went through a lot of this very well in his talk in greater detail than I was going to, which is great, saves me some time and gets the point across even better. So the goal isn't to completely, to claim that the band function is completely useless. If you have a catalog of e-peak values, those aren't going to be necessarily completely devoid of meaning, but it is quite misleading, or can be quite misleading. I think we're approaching the territory of the hammer-nail theorem, that if all you have is a smoothly broken power law, all data start to look single-peaked and with a nice, flat power law, low energy spectral slope. And like Michael said, forward folding is largely to blame for this. And I mean, the low number of count and large uncertainties we often deal with don't exactly help either. So on the right-hand side, you see a figure where I fitted the band function and a physical model to the same data. You see the residuals in the bottom two panels. Now, it's clear that the fits are of similar quality, although this is not. Yeah.
John, are you moving your slides?
No.
You didn't change your slide. Okay.
Not once.
Not once. Yes.
I'm still on the intro slide.
Yeah, still on title slide.
Well, that is very interesting.
So sorry for
the
interruption, but
sorry, so that's very strange. I mean, it says here that I've changed it. Okay, let me then.
You can use the arrows, I think.
Let's do this one then. Can you see this slide now? Did that help?
Yes, we can see the slides. It looks full screen. Can you try to change so I do not interrupt you when I kind of get
So the slide you see now, does it say empirical?
Yeah, now it's changing. You went to slide 2 and now it's slide 3. Yes, sorry,
right.
Thank you. Go ahead.
Thanks for pointing that out. It seems like Zoom is not playing nice with Keynote today. Well, anyway, this is the slide. Yeah, so the figure on the right-hand side, thanks for pointing that out, shows a fit with the band function and a physical model to the same data. And the residuals you see in the bottom two panels indicate that these fits are of similar quality. Now, this isn't a robust demonstration of the exact, same level of evidence for both models, but it indicates that they're quite similar. Now, but if you were to summarize this spectrum using either fit, you'd tell two quite different stories qualitatively. If you were to summarize it using the band function fit, you'd say you have a single peak spectrum with a low energy power law slope. Whereas if you summarize the fit with the physical model, you say that you have a double peaked spectrum with a sort of slow rolling low energy slope. That isn't a power law. Another complicating but crucial factor, which is something that's been touched upon by several previous speakers, is that fitting in a limited energy range means that comparison of empirical functions with the corresponding asymptotic values of a physical model is not necessarily a valid argument. In the case presented here on the right-hand side, comparing the asymptotic value with the low energy slope of the physical model with the alpha value of the band function misses the point by quite a wide margin. An advantage of using physical models is also, of course, that you might be able to differentiate between, say, these two fits on the basis of their, on the parameter values. So if for instance, a physical fit had you find a Lorentz factor of 10 to the 5, this will clearly cast some doubt upon the validity of this model as the data generating process. That you cannot do, again, with empirical functions. So let's have a look at an example of using two physical models. In the case on the right-hand side here, I've generated data from a model of sub-photospheric dissipation, that's the green model, and then fitted both this function and a model for optically thin synchrotron emission, that's the green model, to this simulated data. And I'd like to point out two things. First of all, both models yield quite good fits, and I'll take a pause here and just immediately concede that this is not a good representation of the data, and it's definitely not a robust demonstration of the quality of the fit, but for the purpose and the point I'm about to make, I think it's good enough. Now, unless you can exclude one of these models on the basis of the parameter values, you're sort of out of luck. You can't really say which fit is the best necessarily. And the point I want to make then is that it doesn't, and I think this is really obvious, but sometimes it's easy to forget perhaps, that by demonstrating a good fit to data, that's not enough to show that you've found the underlying data generating process, that your model is the correct one. Secondly, so just outside of the GBM energy range, the models make distinct predictions by which you could discriminate between them. And you'd expect this to happen at just looking at a sufficiently large energy interval, unless that the models are completely degenerate in terms of their spectral predictions. This obviously happens as well above 1 MeV in this case, but there the data are so sparse, there is no statistical significant foundation to make a claim for either model. However, in the subtly egg-shaped outline region at low energy, 0.3 to 10 keV or so, we have XRT data sometimes, which is the topic of this talk, apart from me talking about why we should fit physical models. Before we move on to the XRT data, let's take a brief look at the model that's used here. And it's a model for sub-photospheric dissipation. It's a scenario based on the fireball model. Asaf went through this very, very well yesterday. But in the case study here, essentially, we assume some general dissipation or heating mechanism that transforms some of the kinetic energy of the outflow, some fraction epsilon d of that, into thermal energy for the electrons. And then these interact with the photon field below the photosphere. And at the photosphere, the spectrum decouples. So we simulate this scenario using a code by Asaf Pair. Now, the drawback with this code, and this is true for most all like non-analytical simulation codes, at least at the moment, is that it's time-consuming to run. So, and when you perform fits, we all know you need to make a large number of model evaluations. And the fact that this creates an untenable situation is perhaps the main reason why we have resorted to empirical models in the first place. One way around this problem is to use something like a table model scheme, where you interpolate in a grid of model spectra, spanned by your parameters of interest. You can then evaluate the model to your heart's content inside the convex hull of your grid at a very low computational cost. This is one way of getting around the large computational cost of these simulation codes. And in the work presented here, I've used a model spanning 3 dimensions only. It's the Bolt-Lorentz factor, the isotropic equivalent luminosity, and the fraction of dissipated energy. And this implementation, this limited implementation of this physical scenario, I've called DREAM. So let's move on to the data. I'll be quite quick through a few slides. The data in this work consists of all gamma ray bursts observed before November 2018, with a known redshift and at least 5-second overlapping observation between Swift XRT and Fermi GBM. The data are binned using Bayesian blocks with a significance cut of 3 sigma, and this yielded a total of 32 32 time bins over 8 GRBs. The data were analyzed using PyXspec and in a Bayesian framework. The posterior was sampled using PyMultinest, and then we added posterior predictive checks, like Michael talked about in his talk as well, for a goodness of fit to evaluate the quality of the fits, because again, we can't infer physics from a poor fit. And apart from making sure that our inferences about the physics are sound, we also know, given the limited scope of this implementation, that we are going to find fits that fit. We know this from previous work as well. And it's important that we identify these in a consistent manner to help us with the model building. So let me quickly talk about the goodness of fit. Michael already went through this, but we chose a posterior predictive p-value as a means to evaluate these fits. Now, this is not the most flexible of goodness of fit measures, nor is it the richest, but it does provide a simple rule for accepting or rejecting fits by giving us this Bayesian generalization of the traditional p-value. So what we do is that we assume that the fitted model represents the true data generating process, and we draw replicated data or simulated data from the posterior predicted distribution and compare it to the observed data by comparing the fits to the replicated data to the fit to the observed data. And then if the observed value is large with respect to the simulated, or the fit to the simulated data, then we can conclude that it's very unlikely that the observed data were generated from our model. Now, what about the results then? Quite easy. Half of the fits were successful and half were not. And no GRB was convincingly well described throughout by the model. So let's look at that in some greater detail to see what that means. Now, due to the small number of bins analyzed, because of the sparsity of the data studied, it's very hard to robustly correlate good and bad fits with GRB properties. So I've taken out 4 examples here. The first one, 10.08.14a, has only 1 analyzed bin. That's not going to be very interesting on its own. 14.02.06a was rejected already before we added the XRT data. So we knew from a previous study that this burst was not well described by this current implementation of our model. 15.10.27a has this fairly well-studied additional blackbody component. So when the XRT data becomes bright, presumably the host of this additional component, is no surprise that our model fails there. But the interesting one is 14.05.12a. It's the only burst that was consistently well described by the model before we added the XRT data. But once the XRT data were added, 2 bins, the 2 brightest bins, were rejected. So this seems like an excellent opportunity or an excellent case to study to determine the impact of the XRT data, what happens. So if we look at fits to the first rejected spectrum in this burst, these figures show the 1 sigma posterior credibility band in count space for for this rejected time bin of this burst. And the left figure shows a fit to only GBM data, and then the XRT data in magenta have been added post-fit and the corresponding model predictions as well. And on the right-hand side, we see the fit to all the data jointly. And what we see here is that the XRT data represents an excess of photons at low energies with respect to the model prediction when only GBM data are used. And when the fit is performed with XRT data, the model tries to adapt to this requirement of additional photons at low energies, but it fails because you basically damage the fit in GBM energy range sufficiently to make it a poor fit. Now, this only happens in this burst. In all other bursts, these are the only 2 bins actually that are excluded when we add XRT data. So most of the time the model is flexible enough to account for this excess of photons vis-a-vis the original fit. So there are more results, but I want to talk about something else as well. So let's move on to the interpretation of these results and sort of summarize them. So firstly, as expected, DREAM in this format is not sufficient to describe all spectra observed here, but neither could the XRT data rule out the model with any consistency. To begin to be able to rule out the scenario considered here, or to find more evidence that it does work, would require a larger study of the parameter space, or the inclusion of some probably relevant physical effects like high latitude or off-axis emission. Secondly, this high, low energy photon excess in the XRT data with respect to the original fit, and the fact that in the two models or the two fits that failed when these data were introduced, it seems like one of the unused parameters in the model, epsilon b, which governs the degree of magnetization during dissipation, might be able to simply resolve this problem because it can yield photons at low energy without really mucking up the spectral shape at higher energies. So that is sort of the clear indication of where to look next. But before I end, I want to segue into my current work by asking the question if there is a way to constrain this model, or photospheric models in general, which do suffer, as it was discussed yesterday, from poor predictability. So that this does not turn into a large and expensive parameter sweep or a hunt for yet another second-order effect, probably relevant second-order effect, but still these additional physical effects. So one way to do that is, of course, to add more data, like polarization measurements discussed yesterday and today, or to combine measurements from different wavebands. The idea being that the larger range we cover, the greater the probability that the model deviates from the data beyond what the search of reasonable parameter space or off-axis emission can repair. And the idea I'm currently exploring is to combine prompt and afterglow models to be able to demand a consistent picture across a much bigger domain, both temporally and energetically. So by tying together, for example, the luminosity from a physical prompt emission model with the energy budget of a physical afterglow model, and put these under the same statistical framework and fit them simultaneously and jointly, all physical models, I hope to drive new and better constraints. And hopefully this can get around some of this sort of chasing after the next part of the parameter space. So this work is underway, looks very exciting, but unfortunately I have I have no new results or no results to show from that yet. So I think I've hit my 15 minutes. I'll leave you with a conclusion slide and I'm happy to accept questions.
Okay, thank you, Bjorn, for the presentation. So do you have questions? Please raise your hand. Michael has a question. Yes, please go ahead.
Hi. Yeah, thanks for the talk, Bjorn. On your slide 4, I was very curious about the spectrum.
Yeah.
Okay, so this is not the count data that you're displaying. It's new data points, correct?
Yeah, so a poor representation of the data in reality.
Yes. Do the new data points come from the synchrotron fit or the photosphere fit?
The photosphere.
Okay. So you don't have the residuals because it's also missing between 1 and between.
Yeah.
So you don't have the residuals. It's just overplotting on the new data points.
Yeah. So the data have been generated from the photospheric model, and then both the photospheric model and the optically thin synchrotron emission model have been refitted to the simulated data, and that in new is shown. Yeah.
Okay. Yeah, because I was just curious about the brightness of this because I tried to reproduce this result, but I don't have the residuals. But you can see there's like a really huge difference in the curvature around like 100 keV to 1 MeV. And this we can so at low energy, we do have an ability to distinguish some models, but there at the brightness, you really can see the difference in the curvature. So it'd be interesting to see the residuals from this this fit, to know how well this is and how bright the GRB is.
Yeah, I don't have them here. It's from Zeynep's paper from 2020, I believe, or maybe 2019. and unfortunately, I don't have the residuals handy.
Oh, okay, cool. Okay,
and like
thank you.
this was the main point here was to argue for the inclusion of XRT data in this case.
Okay. Yeah. Okay. Low energy.
I mean, that's really where the model predictions differ greatly, and
right.
XRT data generally have a high number of counts and can resolve this kind of degeneracy when it arises. And then the question of the actual level of degeneracy here, I guess, is a relevant but still different question.
Cool. Thank you.
Yeah. Cheers.
There is another question by Merlin, please.
Yep. So thank you for the talk. You brought up polarization towards the end.
Yeah.
Can you explain a bit more what you're planning to do with that in your future work? Like how you plan to include it, or?
Right. No. So
okay.
My point being that I think what you're doing with Polar, and what you are going to do with Polar too, because you're still involved in that, right?
Mm-hmm.
Is great. It's not at the top of my to-do list to look into this myself. It was more like I think polarization is great. It's going to be a great tool to help bring predictability into this very sort of degenerate model space.
Okay. I just more understood that you were planning to use it as one of the extra parameters to fit. Since you're already doing a joint fitting of two instruments, you could add polarization data to it as well.
I mean, I'd love to. I haven't looked into it, and I'm sure I'll need some need, or at least appreciate some guidance on this. But it's nothing I have planned.
Okay, thank you.
Yeah.
Okay, is there other questions? I don't see anybody with a question. So I actually have one. In those bursts that you're looking for, you need data from XRT, so they are basically very long bursts, right?
Yeah.
Well, I mean, you need 100. Say you need 100 seconds, 70 seconds at best.
I think some of them are even shorter than that, but maybe I'll can look that up.
Okay, my question to you is that so this was something that was actually looked for by Ogayessia and Ravazio, and they were actually looking at using the XRT to constrain synchrotron emission, right? So somehow you are planning to do the same thing, right? But then you actually need to have photon emission processes there, right? So basically you are lacking photons. And my question is, so in principle, you want to do that by synchrotron radiation, or how are you planning to do this?
Yeah. So, I mean, first of all, generally speaking, even if you found an excess in the of photons at low energy from the original GBM fit, this could often be accounted for sufficiently well by the existing parameter space. Like the luminosity tended to decrease a bit, which seems very counterintuitive given that I just said we have an excess of observed photons, right? But the degree of dissipation went up, and given the interaction between these parameters, that yielded a higher level of photons at low energies. Now, that wasn't always a flexible enough process, if you will, but looking at the available parameter space in this implementation of the model, epsilon b, this magnetization parameter, provides us with a population of lower energy photons without resulting to changing the dissipation fraction or luminosity too much. So yeah, that's the idea, is essentially to use barely optically thick synchrotron photons.
Okay, thank you very much. Yeah. So if there are no other questions, then we'll try to have Liang to give his talk. Everything is ready on your side, Liang?
Yes, now the problem has been figured out. Sorry.
Okay, perfect. Okay. So then, Liang, the stage is yours.
Yang, everything okay?
Sorry, I need to close my computer and restart again.
Yes, sure, you need that. Okay, we'll wait for you, please.
Okay, thank you. Sorry.
While we are waiting for Liang, I just want to say a few words. This session is actually quite popular. Apparently, we almost reached 30 participants at the peak, so it's a pleasure to see so many people interested. And I think we will probably have still some time at the end for some short discussion, similar to one we had yesterday. So please stay tuned, and then we can exchange some idea possibly. Okay, Jack is back. Okay. Yeah, if there is still problem continues, you can give a talk from my place. This way we save time. Do you mind? You should have started from this place, I mean, after all. Okay, let's do, so just a second, I switch off your video from there. Okay, so everybody can see you actually here. Anybody can see the screen? Could you confirm, please? Hello?
Yes.
Okay,
Yes, it is
thank
visible.
you. Thank you. Okay, we just a second. Just a second, we switch on your oh, just a moment. Okay, anyway, let's do that. Look, please start. Okay. But please do. What's wrong again? Let me try. Okay.
Sorry for for the problem. So okay, my talk focus on the basin time resolution truncated of the multi-process gamma reverse and variation of the emission property among process. So my corroborated Felix, Asaf, and David and Julie. And this my talk is based on recently published papers in IPJs. So this is my outline. I will first talk about motivation, and then the sample selection and the data analysis, and the observation probability and amount process, and the compatibility with the emission models, and analysis, discussion, and conclusion, and summarize. So motivation is we want to use the Fermi multi-process approach to investigate the observation and emission probability among process with neural course. So this is the start Fermi experiment. The Fermi experiment was launched since 2008 and has triggered more than 2,000 gamma bursts. And our initial process selection, we want to search the gamma river that the ideal case is that the pulses between pulses are separated very well without completely independent. This is an example of this is an ideal case. However, so there are more common observation is that the pulses might be have the slight overlap each other. So we require the minimum flux is less than the peak flux of each process. So therefore, after this step, our initial process selection, including more than 120 boards that had at least 2 clear initial EPA sources, then we define this as our initial sample. So in order to fight to study the time resolute spectral analysis, we should make sure each process, each independent process has enough photos. Then we like to perform the spectral fitting and also calculate the significance of central ratio for each process. So before doing the spectral fitting, before we first should to select the detector, the source, and background. For the detector selection, we follow the common practice, choose the trig detector that have a unit angle of less than 16 degrees, and typically 1 to 3. So that and one BGO detector aspect. The source selection is the period of the GRB emission that is considered is in the most case somewhat longer than T19 report in the GBM catalogs. This is done so that all the relevant features in the net curve can be incorporated. The background selection will select one interval locate 10 of the seconds before the trigger come, and one interval located 10 of the seconds after the emission has ended. Then our next step is using the basin block, the method to rebuild the TT ladder, and several previous works suggest that in order to ensure that the model permit convergent properties are aware of the significance like 15 to 20 is needed. So we therefore only select the basin block time being that have significance greater than 20. So then After these steps, then we define all the selection criteria. For the pulsar selection criteria, we require at least 4 time beams with significance greater than 20 for each individual pulsars. For the burst selection, we require at least 2 such pulsars within a burst. Then all the sample for the reduced to the 39 bursts and can be grouped into 3 subsamples. The golden sample is low overlapping and the pulsars are completely independent. And the silver sample is a slight overlap. And the bronze sample is pulsar. There are 2 that have less 4 time beams meet the criterion of significance greater than 20. So therefore, total sample including the 170 pulsars and including more than 1,000 spectra and from 39 bursts, of which we still including 103 pulsars have the significant significance greater than number of the time spectra of the significance greater than 4. Then consisting of the 944 spectra. Then this we summarize our group property in table 1, including the for each burst, including the redshift and the duration of the each burst and the detectors, use detectors and the source intervals and the background intervals and the number of the spectra greater than total number of the spectra and the number of spectra greater than 20 and the number of the pulsars, total number of pulsars and the number of the pulsars greater than 20. So statistically, our result, including all the sample consists of the number of the 39 and 24, and for the pulsar 1, pulsar 2, and something like this, and pulsar 6, and corresponding the sum consists and 338 and 361 for P1, P2, P3, and this plot saw the result for the left panel. We show the number of the pulsars for each pulsar positions. The right panel will show the number of the spectra for each pulsar positions. Then the next step, we use the two standard GRBs spectral models. One is the Banner function, another is Catapult function to fit in all the spectra that satisfy the criterion that have significance greater than 20 for each spectrum. The Banner function we including the 4 model parameters, and the Catapult less than 1 and including 3 model parameters. Then for each burst, our fitting results are summarized in this table or in tables, including the time intervals of the each basin block selected beams and corresponding the significance. Then the fitting result for Catapult and the fitting result for Band and their difference, and also the energy flux we also compute. And also we have loaded the previous work suggests in some cases in GRB spectrum the Catapult is better, but in some others might be the high energy power significantly improve the fit. So for a given spectrum, we therefore use the divisive information criterion to compare the models. We define the perfect model for a given process is defined by the difference, the DNC, but the difference between the bound and the cutoff is greater than -10. So then we, based on the perfect models, we then investigate the parameter distributions, including the low energy, alpha index, and peak energy, and the energy flux, and the duration of the process. So we summarize our result in the table 3. We found the general trend that the process becomes soft over time. We also use the PS test to check whether this distribution are truly different from each other. So we like to invest in studying the parameter evolutions. The several previous works show that the hard to solve or fluctuating patterns are two dominant patterns in GRB spectral evolutions. In our work, we wanted to investigate these spectral properties among the process within a burst. So we summarize our result in table 5. For compared to the previous several works, we find that our results are similar to the previous works. Is that the hard to solve and the fluctuating are two dominant patterns. However, the biggest new discovery in our paper is that we found that the fluctuating patterns, the fraction, is much higher than the result found in previous weeks, like the Davis paper in 2008 and several early results. So we the next investigated the parameter correlations. We found that there are three main types. The first is more monitoring correlations. This is including three sub types, and the others is two post-wise monitoring correlations compared at the break. The third one is the locally antenna. We defined as the third one. So the main result of the main result is for the parameter correlation is found in our work is that a positive correlation is most common for the FF and FEP relations. However, for alpha EP relations, both the positive and negative correlation are equally common. This result is similar to the result found in Davis 2008 with the single pulsar starting with on the single pulsar first. So then we summarize all the pulsar-wise properties of our sample in table 2, including the pulsar length with depend on the pulsar locations and the source duration for each pulsar positions and the number of the total spectra and the number of the significance greater than 20th, and the pulsar grading we defined before, and the perfect spectral models and the perfect physical models and the evolution type of evolution patterns for EP, both EP and alpha, and following the relations. Okay, this is more. So our axis, we want to assess the compatibility with the emission models. We select the maximum value of the low energy index for each individual process and corresponding the data bin of the peak energy for each process, and then we plot the alpha max against the peak energy, and the different lines are predicted by different physics models. This SCS lies is simulation by the Borges paper 2015, and this line is alpha about equal to the minus 1.6 facts of 5 studied in the Julie papers, and the above the top one is the line descriptive photosphere model predict. We found that there are good function in the initial process above the minus 1.5, consistent with the photosphere models. Even of good function above the NDP lines. So this function is decreased with the pulsar positions. So our likes, there is interesting, quite interesting questions is how multiple proposed compared to the our result with the single pulsar burst. We therefore compare our result with the single pulsar burst defended in David 2008. We found in a group, we found the peak energy on the fluence of approximately double for the multiple pulsar burst, and the low energy index distribution is the shift to the soft values for the multiple pulsar burst, and the E-peak and the beta values are similar between these two samples. So we therefore summarize our result in these tables. So we can the table lists how many bursts in each samples, and we compare to the duration, fluence, peak of flux, peak, alpha, beta. And the likes we want to compare make a similar compare, but based on the time result analysis, because the only compare we focus on the time integral. This time we wanted to compare the result with the time resolution analysis based on the time resolution. The bigger news we find the average alpha values of the initial pulsar in our multi-pulsar samples is similar to that of the single pulsar samples, and the later pulsar positions is pulsars is shorter than the initial pulsar, also shorter than the single pulsar samples. So this is summarized. We have systematically analyzed the multiple pulsar bursts detected by Fermi GBM. It's first 11 years of the mission. We investigated the observation and the emission properties among pulsar with the burst using this sample. We found that the general trend pulsar becomes soft over time. We also found that there are large fractions of the flux tracking is compared to the transition result. We also found a positive correlation is most common for F-alpha and F-E-peak relation. However, for the alpha E-peak relation, both positive and negative correlation are equally common. We also use the maximum value of the spectral parameters of each pulsar to assess its compatibility with the emission models and find a good function of the pulsar is consistent with the photosphere models. Photosphere emission is typically found close to the trigger time, where the synchrotron emission is directly observed at late times. we also compare our sample with a single pulse sample. Globally, we found that peak flux and the fluence are approximate double for multiple supports. And alpha distribution is soft values for multiple supports, where the EP and the beta values are similar between the samples. Based on the time resolution analysis, we found the average alpha value of the initial pulse of the multiple sample is similar to that of the single pulse sample. Okay, thanks. That's all. Hello, Dami. I finished.
Thank you. Yeah. Sorry, I was thinking Gregory was here. So thank you for your presentation. Is there any questions? Yeah, I'm still here. Yeah. I was asking if there are any questions in the audience.
You cannot hear?
Ah.
Sorry. Can you hear now?
Yeah, we can hear you. Yeah.
Okay. So is there any question?
I don't see any. No.
Okay, no question. Thank you, Dami. Thank you. Sorry the problem.
Oh, no problem. No problem at all. Okay. Well, I think we've done with the talks, right?
Yeah, we finished all the talks. We finished the session as well. It was very interesting, very diverse talks.
Yes, I think I've seen few people joined us. Actually, Felix is here apparently. Hello. Well, we still have some questions. If anybody likes to say a few words, please, you're welcome. You can just, otherwise we simply, I mean, it was really a great session and quite a lot of attention. I'm not sure I can see anything what is going on.
You are still sharing your screen. You need to interrupt.
Oh, sorry. Yes, that is the problem. Sorry. Yes. Sorry. How can I stop? Okay. Okay, here I am back. Okay, sorry. Good. So I think there were quite a few interesting points during this session. Let me see, I made notes. In particular, I managed at least to hear a couple of talks, fortunately, because I'm totally surprised by these organizational problems, unfortunately. But at least the outcome of the first talk of today was quite, I think even yesterday we had this message that everything is quite sensible to the viewing angle. I would like also to bring this little bit up, this issue. So I think we realize that, but it would be nice actually to see even with the with numerical calculations, with the photosphere, with the Monte Carlo simulation, post-processing, whatever, or even better with analytical calculations, the sensitivity of the spectrum, the light curve with respect to the viewing angle, and in particular having this typical, let's say, distribution of observational parameters, viewing angle, in particular what we expect from the traditional model, right? What could we expect? Is this in agreement with the observations or not? And in generally speaking, this discussion between Michael and Asaf was quite nice in a sense. I don't know if you like to resume it, but it was quite nice because this is essentially a discussion between theoreticians and observers. people who are driving the data mining side and people who are looking from the observational point of view. And I agree with both sides actually, because it's really essential to understand data well. I fully support Michael and all people working on data, because without data we would not be able to do anything, just having our models in mind, right? But at the same time, we having said that it's important to have some kind of general picture in mind about possible models, about possible implications, relations with other fields. So this particular example about two large radii of interaction of the jet with large Lorentz factor with interstellar medium is a very clear example, but there are many. These observational correlations in particular are important to keep in mind. And not only in Toko-Mati and so on, but there are many other correlations apparently observed, right? Which should be, any model, I think, should be consistent with these observations. And then, generally speaking, we are still, I think, far from understanding the prompt emission. I think everybody share this opinion, right? And any progress in this direction is welcome. Anybody likes to say his opinion, viewpoint on these points? Well, I think everybody's, how to say, digesting the information from the talks. Yes, Asaf?
No, just what you said. I think people are still thinking of everything. It's been quite an intense session.
Yes. Well, if nobody is having comments, I'd like to thank everybody for participating in this very strange format. But we hope that eventually next time we can meet in person and discuss further all these issues. Of course, the video of this session will be ready hopefully by the end of the meeting. We'll try to do our best, but we are few people. So once again, thank you everyone. Thank you, Damian, for chairing this session, and hopefully see you next time.
Yes, thank you everybody for giving very nice talks, very nice presentations, and for the good questions. So have a nice week of Marcel Grossman meeting.
Yep. Thank you very much all.
Bye-bye.
Bye. I think what is missing is this, coffee table sessions, discussions over lunch.
Absolutely.
That's absolutely true.
I know, because you cannot say, okay, let's discuss now. I mean, it's more like, okay, let's digest things a little bit, and then over lunch we can come and talk to each other.
But in principle,
or in the evening,
it could be organized by the organizers, right? You have to fill in your, postal address where you live, so they could actually have like a small box delivered for you for a survival kit for the week, right? With biscuits and coffee and whatever you like.
We should organize, also other services possibly than particular childcare services would be welcome.
Yeah, I'm actually sorry. I have this little girl here with me. That's
okay, very nice.
I had to escape at the end of the talk. She's had to go to pick up.
Okay, so still in the afternoon session, I guess.
Yeah.
Yes, absolutely. So,
right.
have a nice day. Bye-bye.